This is the unit that, if people hate one in Calc BC, this is it. So I'm going to do my best to be a good explainer. You need to do your best to be as engaged as possible and ask really good questions, okay? And then I'm going to participate every day, so I'm going to be, I'm going to post my answer keys in the back, and I'm going to be working on doing the questions again so that I'm mentally in it with you. And then as much as I can be, right alongside you thinking through it in the questions, that's what I want to do. If you need me to re-explain a problem twice, 3 times, 4 times, 5 times, that's what I'm going to try to do, okay? All right, it's not that this unit is impossible, it's that if you are not engaged, it is hard to understand, okay? All right, so it says use a third degree Taylor polynomial approximation of e to the x near 0, so 0 is what we're evaluating it at, to find the limit of e to the x minus 1 over 2x, and then compare it to the actual limit at 0, and then answer if your mind is blown. Okay, so we're going to write the Taylor polynomial of e to the x near 0, so we're going to find f of x, and they want us to find the third degree Taylor polynomial, which means we have to find the third derivative. So first, second, third. Okay, so if the function is e to the x, what is the first derivative? E to the x. And then what's the derivative of the first derivative? E to the x. Okay, so that's the second derivative. And then what's the derivative of the second derivative? E to the x, so that's the third derivative. Okay. And then if we're doing the approximation of those near 0, that just means that we're taking 0 and we're evaluating each of these at 0. So we're going to do f of 0, f prime of 0, f double prime of 0, f triple prime of 0. Okay, so f prime of 0 is e to the 0, which is 1. F prime of 0 is e to the 0, which is. F double prime of 0 is e to the 0, which is. F triple prime of 0 is e to the 0, which is 1. Okay? So to do a third degree Taylor polynomial, p sub 3 of x. Now, if it's centered near 0, is it just a Taylor polynomial, or could we call it something else? We could call it a Maclaurin polynomial, because Maclaurin polynomials are exactly the same as Taylor, they're just centered at 0. Okay, so this is a Taylor, aka a Maclaurin. Okay, it can use both titles here. Okay, so how do we start it? We can look back at our notes if we need to. So before, yeah, so we start it with the constant, right? So we start it with 1, okay? Plus, and then what do we have next? Okay, so this constant, or this coefficient times x, okay? And then this coefficient times, over 2 factorial, okay? And then this coefficient times, perfect, okay? All right, so now we have an approximation for e to the x, and we're going to take that approximation for e to the x, and we're going to plug it in for e to the x in this limit. We're just going to plug it in, because that's our approximation, okay? And they said to use that, and we use the approximation near 0, and so this is going to work if we're finding the limit as x approaches 0. So as x approaches 0, we can use this approximation, because this approximation is true when you're plugging in numbers that are close to 0. So if you're plugging in decimals that are very, very small, very, very near 0, 0.001, negative 0.001, that sort of thing, this is going to work. Does that make sense? So I can use it for numbers that are very, very close to 0. If I'm doing the limit as x approaches 0, I'm plugging in numbers that are very, very close to 0. Okay? Yeah. Because I'm not worried about the 2x part, I'm worried about e to the x, as e being like Euler's number 2.71, that's a decimal I can't really work with without a calculator very easily. And 2x something I'm fine with. That's like a nice number, I can work with that. So I'm not too worried about the 2x. I'm worried about the e to the x and the fact that it's a number that's hard to work with. Does that make sense? Okay. So I'm going to take the e to the x, I'm going to replace it, I'm going to say the limit as x approaches 0 of e to the x minus 1 over 2x, and I'm going to rewrite it as the limit as x approaches 0, and I'm going to use this approximation instead. So I'm going to say 1 plus 1x plus 1x squared over 2 factorial plus 1x to the third over 3 factorial minus 1 over 2x. And then I'm just going to simplify this. So what do you guys notice would simplify first? Those ones. Those ones are going to cancel out. 1 and 1 cancel out, okay? And then you've got all this stuff is divided by a 2 and it's divided by an x. We can get rid of an x. So I can get rid of the x on the bottom, and then what happens to the x's on the top? Yeah, so this reduces to a 1, this reduces to an x to the 1, this reduces to an x to the 2. Okay, so if I write down what I have now that I've simplified, I have the limit as x goes to 0. I've got 1 divided by 2, so that's 1/2, plus x over 2 factorial divided by 2. What's 2 factorial? It's 2 times 1, right? So it's just 2. And then 2 divided by 2. 2, think about a 2 on the bottom of a fraction and another 2 on the bottom of a fraction. 4. 4, okay. Are we okay with that? Okay. And then we have x squared over 3 factorial, 6. So we've got 6 on the bottom of a fraction and 2 on the bottom of a fraction, 12, okay? So x squared over 12. Okay, so that's all simplified. And now if we think about doing direct substitution, what do we get? 1/2. Okay. So we just used Taylor polynomial approximation to evaluate this limit, and we got 1/2. Now let's throw away this unit. Let's go back to how we would have done this problem if we had never done this unit before. Okay, so let's go back to the original problem. We've got the limit as x approaches 0 of e to the x minus 1 over 2x. And if we had seen this problem and we had not done this unit before, what would we have done? Say it again? L'Hopital's, yeah, because you would have plugged in 0 to the top, and you would have gotten 1 minus 1 is 0, and you would have plugged in 0 on the bottom, you would have got 0, so you would have had 0 over 0. Does everyone see that? And so if we did that, we would have said, okay, L'Hopital's. So I'm going to show my work, because I always got to do a good job of that. So the limit as x approaches 0 of e to the x minus 1 is 0. The limit as x approaches 0 of 2x equals 0. And so that tells me to use, I'm going to write LHOP because I don't have a lot of space. Okay, so if I used L'Hopital's, e to the x over 2. Okay. And now if I did direct substitution, I would plug in 0, and I would get e to the 0, which is 1. I'd get e to the 0 over 2. Same. Is your mind blown? Is that kind of cool? Nobody? The first time I saw that, I was like, what? What? You wouldn't do it the long way. You would still do it this way. The point of this problem is to show you that this works. That this is a mathematically reasonable way of doing it. And one thing that I learned since teaching this unit is that your calculator actually uses Taylor polynomials. It doesn't use e to the x. It uses Taylor polynomials instead of e to the x. So it just uses polynomials to several degrees, and that's what it plugs in. So it doesn't use sine, it doesn't use cosine, it doesn't use e to the x, it just uses Taylor polynomials to do all those calculations for us. And I was like, we've been lied to. We've been lied to this whole time. I'm very uncomfortable, but I also love it. This made me nerd out in a big way. Okay. Are we comfortable with that problem? We can see that, like, whoa, crazy, it works. Okay. Example 7. There was supposed to be a picture, and it's not here, and I keep forgetting to put it in there. So this is what the picture is supposed to look like. Bloop. This is f of x. Oh, do you like the old guys? Was that like, I was like, these fancy notes. You know, I spent some time making these notes good. It's like we're getting some history in here. Very professional. But let's just be real here. We know that white guys did not come up with all of math, right? White guys are accredited with all of math, and we know that's not historically accurate. We know that, right? White guys do not come up with everything. We know that's like rewritten history. I'm just saying, we know that, right? Can we nod? Okay. I just want you guys to know that, like, that's wrong. That's wrong. Okay, that's wrong. Okay. Somebody else, non-white, some non-white person came up with that, and then a white guy went, oh, that's interesting. I second that, and then his name got put on it. Okay. I just want you guys to know. Of course. We don't know that because it's not as, I mean, I'm sure if you did research, you'd find other names, but that's, if you look more into it, they'll say it's just not as well known. So all the if you look at all like the mathematicians that like everybody's heard of, well, not everybody, that math nerds have heard of, if you look at all of them, they're all white dudes. But if you start to like research math more, then you'll find these really interesting other sounding names of like Chinese men and Polynesian men and whatever men from like ancient civilization-y type things. And it'll be like, yeah, they brought it somewhere that was colonized, and then a white man took notice of it and wrote about it in a book somewhere. And then he was credited with it because he was the first person to write about it and use it in a way that was more well-known or whatever. White men did not come up with everything. And we know there were some women behind that. Okay, let's move on. Okay, so it says we have a second degree Taylor polynomial. We can tell from the way that it is written that it is centered at 0. So it is not just a Taylor polynomial, it's also a Maclaurin polynomial. Okay. About x equals 0, what can you say about the signs of A, B, and C if this is the graph that is pictured? Okay, so if we look at this, I'm just going to kind of interpret the different pieces so that we can figure out what each of them means. So we know that A comes from f of 0. We know that B comes from f prime of 0. And we know that C comes from f double prime of 0. And you can tell that because all I have to do is look at the previous problem and how I created this function, right? So the first f of 0 is how I wrote the first term. So that comes from just the function. And then f prime of 0, that's how I wrote with the x to the 1. That came from the first derivative, and then the second derivative is how I wrote the x squared. So that's how I can just take this constant and then these coefficients and then figure out exactly what derivative they're attached to. Does that make sense? Okay, so if I want to interpret this, f of 0 is just the function evaluated at 0, which is also known as what? The y-intercept. Okay? And then the first derivative on the graph, we're going to see as what? The slope. Okay? And then the second derivative on the graph, we're going to see as what? Yeah, concavity. Perfect. Okay, so let's answer these. We want to say the signs, so either they're positive or negative. Okay, so what do we know about A? Yeah, it's greater than 0 because the y-intercept is above the x-axis. So once we got all that interpretation out of the way, that was a really easy question to answer, right? Okay. What do we know about B? Yeah, B is positive because the slope is positive. C is less than 0 because, why? Yeah, the graph is concave down. Perfect. Not so bad, huh? So once we figured out how to interpret each little piece, it was really easy to know what those signs were. Okay, let's move on to example 8. Typically, yeah, we've seen questions like this before, where you were looking not in the context of a Taylor polynomial, obviously, but you were looking at the graph and you were looking at the y-intercept and interpreting a sign. And then you were looking at the slope and you were interpreting it whether or not it was positive or negative. You were looking at the concavity and interpreting whether it was positive or negative. We've done something like this on a multiple choice problem. I think that the one that we did before, you were comparing f prime and f double prime, and you were saying if you were to write an inequality, which one was bigger or smaller, and it was like one was like maybe the y-intercept was 0 and then the concavity was positive and the slope was negative, and then you have to put them in order from smallest to biggest. And you're able to do that because you're able to say, oh, the y-intercept is 0, so that's in the middle. The concavity is positive, so that's the biggest. The slope is negative, so that's the smallest. So I can put them in order from smallest to biggest because I know, just by looking at the graph, like I don't even have to know the numbers. I can already tell which one's smallest, which one's biggest. Does that make sense? So we've done something like this before, just not in this context. Yeah, good question. Okay, so next problem. Now, from this, we have polynomials that we already know. These are polynomials that we are going to memorize, and these are specifically Maclaurin polynomials because they're centered at 0. These are like common polynomials. They're not going to be common if they're centered at 2 or centered at 3 or centered at 4 or centered at 5 because that's not like a typical center. But as you can imagine, centered at 0 is going to be relatively common, okay? So if we were to flip back and look at some of the ones we've already done, e to the x, we just did an example, hold on, we did it in example 6. We did it in example 6. And so e to the x is one that we already know. That is 1 plus x plus x squared over 2 factorial. And this is like if you were to start a cheat sheet today, I'd put this on it because you don't want to be, I'll probably write it on the whiteboard so that we can just have it in front of us. plus x squared over 3, sorry, plus x cubed over 3 factorial. And then we're going to write plus dot 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 plus. So this is how we say it, like it continues. And then the last term is x to the n over n factorial. So we're going to say that's the nth term. And this is the proper way of writing, you know, it has a bunch of terms in between, and then this is how we get to the last term. Okay. Did we do one with sine? Let me flip through. Cos was 3. Did we do sine? Example 2. Perfect. Okay. So sine, yep. So sine, you can see, starts with x, and then you can see it does the odd numbers. Everyone see that? And it alternates sine. Okay. So sine is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot 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 plus negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. And it looks like this is starting at n equals 0. To be able to get that first term, we'd have to do n equals 0. Yeah. Because we want a 1 on the bottom. Yes. Okay. Okay. How are your brains? Everything make sense so far? Okay. Next one. We've got cos. And if you look at example 3, you can see cos starts with the constant, starts with 1, and then it does the even exponents. So we've got 1 minus x squared over 2 plus x to the fourth over 4 minus x to the sixth over 6 plus dot 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 plus negative 1 to the n x to the 2n over 2n factorial, and this is also starting at 0. And dividing by 2 times 0, 0 factorial is not 0. That's why you're allowed to divide by 0 factorial. 0 factorial is 1. Okay? So just a heads up on that. I know that feels weird because you're putting 0 on the bottom of a fraction, but it's okay. And here, I'll prove it to you. Do you guys know how to plug factorials in your calculator? So hit the math button, you go over to probability, and down to number 4. I don't know. That's a great, we should ask Google that in a little bit. Google could probably tell us. Okay, the next one is a weird one. I do not think that we got to this one in the notes on any example problem. So the next one comes from the geometric sum formula. Geometric sum formula. So what is the formula to find the sum of a geometric series? First term over a sub 1 over 1 minus r. So if it's a sub 1 over 1 minus r, that means that the first term of this series is 1, and it means that the r value is x, okay? So that means that if we were to write out the formula, we would say that we're going to start at 0, because we've started at 0 for all of these. We're going to start with the 0 term. We're going to go on forever, and we're going to have first term is 1, and we're going to multiply by x every single time. Does that make sense? We're going to start off with 1. We're going to multiply by x every single time. Okay? So I'm going to start with 1, and then I'm going to multiply by x. What do I get? X. Okay, I'm going to multiply by x. What do I get? I'm going to multiply by x. What do I get? I'm going to multiply by x. What do I get? Okay. And then if I, oops, I needed another plus sign there. Let me write this correctly. Okay, and then what do you guys think the nth term is? X to the n. Okay. It doesn't need a factorial. It's different than sine, cosine, and e to the x. It just works out differently than those. If we were to write these out, yeah, there would be a coefficient that would cancel out. The way the coefficients work would cancel out the factorials on the bottom. Yeah, good question. Okay, so do we see how, this is kind of the proof for how it works, but do we see how this is the sum, and how that sum would give us this, and how that would give us each of those terms? Okay. So we are going to make sure, I mean, it's part of your cheat sheet requirements anyway, but we are going to make sure that this ends up on our cheat sheet. We are going to memorize these, though, because these, they got to be memorized. You're going to use them enough that you're probably going to memorize them anyway, but they do have to be memorized. Okay. So it says, using the above polynomials, find the first 4 non-zero terms of the Maclaurin polynomials for sine of 2x, x times cos x, and 4 e to the x squared. So we're going to write that out. We got 3 problems we have to do, basically. So if you have g of x equals sine of 2x, then we're going to take the first 4 non-zero terms, so we're taking these first 4 terms, and instead of writing x, where all the x's are, we're going to replace it with 2x. Okay? So we're going to say g of x is 2x minus 2x to the third over 3 factorial plus 2x to the fifth over 5 factorial minus 2x to the seventh over 7 factorial. Now, it does not say that you have to find the nth term, but sometimes it will. Sometimes it will say find the nth term, and then you would just plug in the 2x for the x in the nth term, and you would simplify that as well. Okay? So we can leave that here. We can simplify that. So if we simplified it, we would say 2x minus 2 to the third x to the third over 3 factorial plus 2 to the fifth x to the fifth over 5 factorial minus 2 to the seventh x to the seventh over 7 factorial. This is one of those things where how much you simplify is relative to you, relative to the problem. Is it multiple choice? Are you looking for a specific multiple choice answer, or is it an FRQ? If it's an FRQ, I would not go any further than plugging it in. I'd plug it in and stop. If it's multiple choice, I would go as far as I need to recognize the multiple choice answer. Okay? All right. Next one, it says f of x is x times cos x. So what I'm going to do here is I've got x, and I'm going to multiply it by cos x. So I'm going to write out the first 4 terms. X times cos x. And then I'm going to take that x and I'm going to distribute it inside. So distribute. And I get x minus x to the 3rd over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial. How are your brains? Good? Okay. All right, next we have h of x equals 4e to the x squared. So what do you guys think we have to do with this one? Square the whole polynomial? Just the x, okay. And multiply the whole thing by 4. So we're going to take the x's in the polynomial and we're going to plug in x squared. So we're going to take the x in the polynomial, we're going to plug in x squared, and then we're going to put a coefficient of 4 in front of the whole thing. So h of x is 4 times 1 plus x squared plus x squared squared, over 2 plus x squared to the 3rd over 3. And then that's 4 terms. So I've got 4, and then I plugged in x squared. Okay. So I am going to distribute the 4s. So I've got 4 plus 4x squared plus 4x to the 4th over 2 factorial plus 4x to the 6th over 3 factorial. Again, you can simplify as much as you want or as little as you want depending on what the goal is. So is it an FRQ? I would simplify hardly at all. Is it a multiple choice problem? I'm going to simplify as much as I need to see that the multiple choice problem. I like to simplify enough so that I can still see the patterns. So I can still see the factorials, so I can see the 4 that I plugged in, so I can see the exponents that I plugged in. It kind of depends on what the outcomes of the problems look like, what I see. Okay. Any questions? Yes.
So the polynomial stuff is just like another way to write the equation?
Yep. Yep.
So you're just saying like sine of x is...
Yeah, so if we took this, 4, so we had 4 e to the 0.01 squared, we get that, okay? Now, I'm going to do 0.01, I'm going to store that as x, okay? And now I'm going to plug in 4 plus 4x squared plus 4x to the 4th divided by 2 factorial plus 4x to the 6th divided by 3 factorial. Same number. Approximations that are easier to get by hand. Mm-hmm.
Why would they ever make you do
It's, well, like I said, if calculators are already doing this, the benefit now is we are training up students who understand the the way that complex equations are broken down into simple polynomials. Because this polynomial is not crazy, right? So I'm showing you the math behind how you can take a complicated, e to the x. It looks simple, but it is kind of complicated the way it works. Sine of x, cos of x, how we can take something like that and how we can use calculus to break it down into a polynomial, which the parts of a polynomial are much simpler. So I'm training up a group of students who understand how that works, and I'm giving you like the elementary ideas. So that if you chose to go into a field of mathematics where you guys are the ones creating calculator programs, you would understand the basics of how it works. And then if you wanted to get deeper into it, you would understand this is how it works, now we build on that. Does that make sense? So like, it's good for that sort of thing. Are you gonna do it in your life? Probably not, because you're probably, are you gonna be a mathematician someday where you need to do that? I don't know. I've done some really weird calculations by hand to get around not being able to do some of these things. Like, I'm like, oh, I don't, like a really oversimplified example is saying, oh, E is 2.71, so I use 3 instead. That's a really oversimplified example of like the trick of what you're doing here. Is you're taking something like this and replacing it with something that you can easily work with. We're just getting into much more complicated math now. So we're trying to build basic competency in that in the most promising of students who might continue on and study it. And if not, then, but that's the idea, is that you guys are like, hopefully out of everyone I teach, maybe a few will trickle out and become a certain type of engineer or something, that will one day deal with this. Or else maybe you'll study knots. Who knows? Yeah. All right, let's go ahead and get to the assignment.